So you're stuck in slow traffic. The ebb and flow of cars seems completely chaotic. Drivers switch lanes, brake unexpectedly, and speed up without warning. Yet despite this apparent randomness, traffic as a whole often moves in a surprisingly orderly fashion, and this seemingly paradoxical balance between individual unpredictability and collective order provides an intriguing analogy to one of the most profound puzzles in physics, the divide between quantum mechanics and general relativity. At its core, traffic is a complex system that exhibits a delicate balance between order and disorder. This makes it an ideal subject for studying emergent phenomena in physical systems. When we look at traffic, we're observing the collective behaviour of individual vehicles, each with its own trajectory and decision-making process. These microscopic interactions give rise to macroscopic patterns that we can observe and analyse at larger scales. One of the most widely used frameworks for describing vehicular movement on multi-lane motorways is the R-Rascal traffic flow model. This model provides a mathematical foundation for understanding traffic dynamics by incorporating both Euler and Lagrange variables. The Euler approach focuses on fixed points in space, while the Lagrange approach follows individual vehicles through time. This dual perspective allows for a comprehensive description of traffic behaviour. When we apply symmetry analysis to traffic flow models, we uncover important insights into the underlying structure of these systems. Using Lie group theory, we can identify various symmetries that govern traffic behaviour. These include translational symmetry in space and time, scaling symmetry, and Galilean invariance. These symmetries reflect fundamental properties in the physical world, such as the homogeneity of space and time and the principle of relativity. However, it's important to note that traffic flow also exhibits asymmetries and broken symmetries, which are crucial for understanding its complex behaviour. Our understanding of symmetry in traffic flow systems challenges the traditional notion of symmetry as a rigid objective property. Instead, it reveals symmetry as a fluid and subjective concept, adapting to the observer's perspective and system state. In traffic, what appears symmetric from one vantage point may be asymmetric from another. The symmetry of traffic flow can shift and morph based on factors like time of day, weather conditions, or even the collective mood of drivers. This dynamic nature of symmetry in traffic systems echoes recent developments in theoretical physics, where symmetry is increasingly viewed as an emergent and context-dependent property, rather than an absolute, unchanging feature of reality. The interplay between order and disorder in traffic flow is evident in various phenomena we observe on roads and highways. One striking example is the formation of traffic jams, which can emerge spontaneously even in the absence of obvious external triggers. This phenomenon, known as phantom traffic jams, illustrates how local fluctuations can propagate and amplify, leading to large-scale disorder in the system. But traffic flow isn't all about chaos. It also demonstrates remarkable self-organizing properties. Under certain conditions, vehicles can form stable patterns such as platoons or synchronized flow states, which exhibit a high degree of order. These ordered states emerge from the collective behavior of individual vehicles, demonstrating how local interactions can give rise to global structure. To better understand this balance between order and disorder, we can turn to the sandpile model proposed by Per Bak. This model offers a compelling analogy for traffic flow dynamics. In the sandpile model, the addition of sand grains to a pile leads to an occasional avalanche, which serves to maintain the overall stability of the system. Similarly, in traffic flow, small perturbations can lead to localized avalanches of speed adjustments, which help maintain the overall flow of vehicles. This concept, known as self-organized criticality, suggests that traffic systems naturally evolve towards a state poised between order and disorder. In this critical state, the system is highly responsive to small changes, allowing for rapid adaptation to changing conditions. This delicate balance between stability and instability is reminiscent of quantum systems, where particles exist in superposition states until observed. Now let's look closer at the parallels between traffic flow dynamics and quantum mechanics. Several key aspects of quantum theory find analogues in traffic systems. For example, The Heisenberg uncertainty principle in quantum mechanics states that certain pairs of physical properties, such as position and momentum, cannot be simultaneously measured with arbitrary precision. Similarly, in traffic flow, there's an inherent uncertainty in predicting the exact position and velocity of individual vehicles at any given time. This uncertainty arises from the complex interactions between vehicles and the stochastic nature of driver behavior. Another intriguing parallel is the concept of wave-particle duality. In quantum mechanics, entities can exhibit both wave-like and particle-like properties. We see a similar duality in traffic flow. At the microscopic level, traffic consists of discrete vehicles which we can think of as particles. But at the macroscopic level, it behaves more like a continuous fluid exhibiting wave-like properties. This duality is captured in the R-Raskol model, which incorporates both particle-like and wave-like descriptions of traffic. We can even find a loose analogue to quantum entanglement in traffic flow. In quantum systems, particles can become correlated in such a way that the quantum state of each particle cannot be described independently. In traffic, the decisions and actions of one driver can have immediate and non-local effects on other drivers, influencing the overall flow of traffic. But the insights don't stop with quantum mechanics. Traffic flow also exhibits properties that align with concepts from general relativity. In Einstein's theory, the presence of mass and energy curves space-time, affecting the motion of objects. In traffic flow, we can think of the density of vehicles as analogous to mass-energy density, influencing the space-time of road network. Areas of high vehicle density effectively curve the traffic space, altering the trajectories and speeds of surrounding vehicles. And we can even draw a parallel between traffic jams and the concept of event horizons in general relativity. Just as an event horizon marks the boundary beyond which events cannot affect an outside observer, once a vehicle enters a dense traffic jam, it becomes effectively disconnected from the free-flowing traffic ahead. Even the relativistic effect of time dilation finds an interesting analogue in traffic flow. Drivers often perceive time differently depending on the traffic conditions, with time seeming to pass more slowly in congested areas, much like how time passes more slowly in strong gravitational fields or at high velocities in relativity. So what can all of this teach us about the quantum mechanics general relativity dichotomy? Well, by exhibiting properties that align with both theories, traffic systems offer a macroscopic model for exploring how these seemingly incompatible frameworks might be reconciled. One intriguing possibility suggested by traffic flow dynamics is the concept of emergent space-time. In this view, the macroscopic properties of space and time emerge from the collective behavior of microscopic entities, much as the flow of traffic emerges from the interactions of individual vehicles. This perspective aligns with certain approaches to quantum gravity, which seek to derive space-time from more fundamental quantum processes. The role of information and entropy in traffic flow provides another bridge between quantum and relativistic concepts. The flow of information between vehicles through visual cues and signalling is crucial for maintaining order in traffic systems. This information flow can be analysed using concepts from both quantum information theory and classical thermodynamics, potentially offering insights into the nature of information in quantum gravity theories. Furthermore, traffic flow exhibits scale-invariant properties with similar patterns emerging at different levels of magnification. This scale invariance is reminiscent of the renormalization techniques used in quantum field theory to handle infinities. Studying how traffic patterns transform across scales could provide insights into the problem of reconciling quantum mechanics with gravity at different energy scales. In conclusion, the study of traffic flow reveals a rich interplay between order and disorder, exhibiting properties that resonate with both quantum mechanics and general relativity. By analysing the symmetries, collective behaviours, and emergent phenomena in traffic systems, we gain valuable insights into the fundamental nature of space, time, and matter. And while traffic flow alone cannot resolve the deep tensions between quantum theory and general relativity, it offers a tangible macroscopic system for exploring how these seemingly disparate frameworks might coexist. the balance between particle-like and wave-like behaviour, the emergence of macroscopic patterns from microscopic interactions, and the role of information and entropy in shaping system dynamics all provide fertile ground for developing new perspectives on the quantum mechanics general relativity dichotomy. In the grand scheme of things, the dance of traffic on a Monday morning and the behaviour of particles in a quantum field might be more alike than we ever imagined. Both systems reveal the delicate interplay of order and chaos, hinting at a deeper unified truth that governs the very fabric of reality.